Good afternoon, everyone. Thanks for joining us in this series. So previous video, we introduced the concave and convex mirrors. We introduced their terminology and sign convention. In this video, we're gonna look at the image produced by an object sitting outside the focal point of a concave mirror. We're gonna use ray tracing, which is slightly different than for the lens, and using the thin lens equation. In the next video, we'll put an object inside the focal point, and then we'll have a couple of videos as exercises. So please like, subscribe, share, give us your opinions and comments on these, and maybe requests if we have time and the resources. We will definitely do a few videos that you suggest. So let's begin. Here's a concave mirror, just a little review in terminology. This is the dark side. This is the reflective. This is the focal length. There's the radius. Radius is twice the focal length. Here's an object sits here. This is what we call the distance to the object. And then if we have an image sitting like this, this is height of the image, height of the object. This is what we call the distance to the image. Everything on this side, everything on this side is positive. Okay, in terms of distances, not heights. DO, DI, F are all positive. Okay, on the right side of on the light side of the mirror. All right, so let's look at this one, ray tracing. Ray tracing is very important. So let's see, here we have the focal length is at 1, 2, 3, 4, 5. So F is at 18 centimeters or units. The object, I put it at 30. H sub O is 2 centimeters. And the radius obviously is twice that, so it's 36 centimeters. So now let's do the principal rays for a mirror, slightly different than a lens. So let's begin. A ray coming in parallel to the optical axis is reflected, doesn't go through, reflected through the focal point. Here's the focal point. So here's the ray coming in parallel, bounces back through the focal point. You see that? Second one is green. A ray perpendicular to the lens reflects on itself. Now, from basic geometry, any ray that's going through the radius is basically perpendicular to the surface of the sphere. So any ray going through the center will produce a perpendicular line, and then hits this and comes back on itself. Okay. And then the third one, ray through the focal point reflects parallel to the optical axis. So if I shoot a ray through the focal point, hits, comes back, parallel. And then here's the image right there. And in this case, the image is at 30, 45. So DI is 45, saying positive, because it's on the light side, and it's about HI, it's about 3 centimeters. Okay. Now, there is another ray that people follow. I'm not going to talk too much about it. I'm just going to mention it. It's very hard to get it accurate. And that's a ray that goes to the vertex right here. A ray that goes to the vertex. Whatever angle it comes in at, it leaves at the same angle. So as you can see, it's very hard to make these angles equal, and then that has to actually match the rest and go through this point right there. That's a ray. Again, some people use that ray that goes to the vertex, or right here, the vertex. It reflects at equal angles, but it's very hard to get equal angle reflection without having a protractor and stuff like that. So the other ones have 2 points that has to go through. Has to go through the tip of the arrow and either the center, the focal point, so you know that it's going to be more accurate. All right, so this is what we have. Let's see now what we come up with using thin lens equation. Here it is. So we're given DO to equal 30 centimeters, F to be 18 centimeters. So let's look at DI. So 1 over DI plus 1 over DO is 1 over F. So 1 over DI, bring DO over. Again, it's the same procedure. I'm sorry if I'm boring you with this, but maybe you've seen it for the first time and I'd like to go through it consistently. You get a common denominator. This is 1 over DI. Now bring it up here. So DI is F times DO over DO minus F. Or 18 times 30 over DO is 30 minus 18. So keep it like this, 18 and 30. Don't do anything with those yet. This is 12. So we can easily divide this by 6. Give me a 2. This gives me a 5. And then the 18 by 2 gives me a 9. 9 times 5 is 45 centimeters, which is what we got. Which is what we got over here, roughly. Okay. Now let's look at the H sub I. So look at the magnification here. M is negative DI over DO, which is HI over HO. So I'm looking for H sub I is negative DI over DO times H sub O. So negative DI was 45, DO was 30, HO was 2. And HO is actually plus 2. That's correct. Because it's pointing up. So here we can divide easily by 5 or by 15 actually. So here's a 2 and here's a 3 and 2 cancel out, leaves me with negative 3, which is what we got. And the negative m less than 0 implies that this is inverted and it's 3 centimeters high. Go back again. It's inverted. In other words, it's opposite to what the object is, and it points down. Okay? So let's go back again. Very important. A ray coming in parallel from the tip hits the mirror, reflects through the focal point. It is coming in parallel, hits the mirror, bounces off through the focal point. One is perpendicular to the lens. That means it goes through the center and the tip at the same time, hits the mirror, bounces back on itself. So just one line over there. And then a ray through the focal point. So we're going to have an orange ray coming in through this red dot, hits the mirror, bounces out parallel to the optical axis. These are the 3 principal rays. Wherever they meet is the object, is the image. And this is the data we read off the diagram. This is the DI and the magnification, which basically, actually not magnification here. I'm sorry, this is H sub I is negative. We didn't compute the magnification. We just computed the height of the image. Okay. The magnification is not negative 3. If you want to compute M, is H sub I over H sub O is negative 3/2. It's 1.5 times as large. Okay. Between 2 and 3 is 1.5 times large. But here we computed H sub I. and h sub I is negative, meaning it's inverted, which matches again our ray tracing. Okay, so this is true for any object outside the focal point. Okay, the next video we'll do for an object inside the focal point. We'll have a different ray tracing diagram, and then we'll talk a little bit about some interesting facts about the object which sits inside the focal point. All right, so this is it for this video. Hope to see you in the next one. Thanks for your time, and again, please let us know your opinion and your comments on these videos that we're putting out. Bye-bye.